Hi. So, we have seen lot of process flow for lot of devices, right, and if you see for each device when we fabricate it, it requires several things. First is of course the process flow, second is the recipe, third is the mask because we require mask, right, and then we do the characterization that how the device is operating to understand the efficacy of the device or to understand the performance of the device, or in another term to evaluate the performance of device. So, now microfabrication or microengineering requires a certain set of tools or equipment that we need to use to fabricate those devices, and to name few we have seen we use photolithography. It is also called a mask aligner, right. We use e-beam lithography, we use thermal evaporation, then we go for wet etching, we go for dry etching, again dry etching we have seen RI which is reactive ion etching, DRI deep reactive ion etching, and then we also go for PECVD, LPCVD, APCVD. So, the point is that all this equipment, the usage is costly. When you make devices in bulk, it becomes cheaper. Okay. So, before we fabricate a device, is always good to perform simulation, and the simulation will help us that for the given design or for the design that we have chosen for a particular device, how it will work. That means, let us take an example of a strain gauge. If I apply a 0.5 Newton of force to the strain gauge, what is a strain or what is a bending or what is a displacement or the force transferred to the strain gauge such that the resistance would change or the deformation would occur. To understand the stress or the strain in that particular device, we can perform simulation. To give a second example, if I have a heater, a micro heater, if how the power versus temperature correlation can be obtained. For example, if I use 100 milliwatt of power, what is the temperature that heater will reach to? How we will know, right? So, simulation helps us to understand for the given design what will be the performance, and then you have to go for fabrication. If you stick to all the parameters correctly, then the simulation results and the fabrication and the characterization results will be close to each other, that will follow each other. If the recipe is not properly followed, if the fabrication during the fabrication, if the process is not properly followed, the simulation results will vary compared to the fabrication and the performance of the device. So, for today let us see what kind of simulation tool we can use, and I will take an example of a heater. Okay. So, the tool that we are going to use is called COMSOL multiphysics. It is a company, a well known company, Swedish company, and the usage of COMSOL is really high. Now, that does not mean that this is only simulation tool, there are other simulation tools as well. All right. Now, do not get confused with Cadence and COMSOL. See, Cadence is for circuit design, COMSOL is for simulating a micro electromechanical sensors or a micro sensors or a transducer. All right. So, today let us see how we can perform simulation for a micro heater. All right. So, if you see the screen, it is the heater electro-thermomechanical simulation using COMSOL multiphysics, and the process generally is. So, you can see what you can do, you can use electrical potential you can have temperature plot, or you can also have stress distribution on the chip. So, if you see this structure, right, this structure is a heater, and based on how much voltage you apply, the change in the current, and based on the change in current or flow of current, the heater will heat, that you can simulate. You can simulate what is the stress over the pattern when we follow it, right, what is the stress, and so on and so forth. So, let us see the first example, and I will show it to you how to perform that simulation. This again, this topic we have taken because of the questions raised in a forum, that the most of the students, they want to learn how we can perform simulations, because they do not have all the facilities available for fabricating the device. So, the process will consist of a model wizard, how to create the geometry, what are the materials that we can select, what is the physics behind it, how to mesh the design, and then study and post processing. So, this is just an example of temperature plot on surface of a circuit. You can just select this as a silicon oxidized silicon chip, and this is a material on which you can select this material as a nichrome. Nichrome is NiCr. You can also use nickel, you can also use gold, you can also use platinum, and there are list of materials that you can use to fabricate the heater. Alright. So, once you fabricate the heater and you apply a power to this end, let us say we apply some power, then depending on the resistance of the heater, there will be flow of current, and that will generate the temperature, and the temperature distribution plot is shown on the slide. So, what is the problem definition? The problem definition for this class is that we want a heater made up of nichrome, right, which is deposited on a glass plate, and we want to control this heater circuit to a temperature which we have desired. So, we need to maintain this temperature. Electrical potential we have to apply to nichrome, and the rise in temperature is due to the Joule's losses, I square R losses. I told you that when you apply voltage, there is a flow of current, and because of the resistance there will be loss, which is Joule's heating, and that losses are I square R losses. The temperature rises leads to thermal expansion, right. So, like I said, we are interested in understanding the effect of applying a power to a heater, and understanding the heating and the power losses as well as the stress in the film. Now, what we have used? We have used nichrome, right, and we all know how to fabricate a micro heater, right. Just to help you out, you take a glass substrate, right, on this is a glass on which you can deposit nichrome, and you perform lithography. How to perform lithography? You can deposit. So, this is our nichrome, you can deposit photoresist, right. You pre-bake it or soft bake it, and then you use mask. It can be bright field mask or dark field mask depending on what pattern you want. After mask, what you can do? You can expose with UV, right. After exposure, you have to perform the photoresist development. When you perform photoresist development, what you get? You get photoresist on this particular area. This is your photoresist, this is your nichrome. Why you have only photoresist in this area? Because your mask was a bright field mask, and the photoresist that we have considered is a positive photoresist. So, the area which is not exposed will get stronger, right. Once you have this, you can dip this wafer in nichrome etchant. Nichrome etchant. When you dip this wafer in nichrome etchant, what will happen? That you will only have nichrome below the photoresist, right, and this is because photoresist will act as a mask. Photoresist will act as a mask and save the layer below it. After this, you deposit the this glass with nichrome and photoresist in acetone. When you dip this wafer in acetone, not deposit, sorry, you dip the wafer, okay. You dip the wafer in acetone, what will happen? It will strip off the photoresist. So, it will strip off the photoresist. When you strip off the photoresist, what will happen? You will be having a nichrome heater on the glass. That is what is shown here, okay. That is what is shown here, and this is just an example where there is a glass plate, there is a electric heater, and if you heated fluid stream, if it is a hollow plate, or there is a space for the liquid to flow, and if I flow a hot liquid, right, then what will happen? What will happen to the heater? All right, this is just an example. This we are using silver pads. You can use a chrome gold as a contact pad. Instead of nichrome, like I said, you can use multiple materials. Okay. So, when you open COMSOL multiphysics, you can start with new model wizard, and then you can select a space dimension. You have to select a 3D as a space dimension. After that, what is the next step? Next step is that you have to understand your physics, and what you want to understand? You want to understand electric currents, right. So, you are selecting electric currents, and then in the heat transfer, what you understand? You want to understand heat transfer in solids. So, you have to select heat transfer in solids. So, now we have selected two things, one is electric current and second is heat transfer in solids, that you can see exactly on the GUI, where you can see the physics interfaces that you have added would be electric current shells and heat transfer in solids. After this, what is the next step? Now, you see you have the choice of adding multiple physics interfaces. For example, if you want to understand magnetic field, you want to understand the rotating machinery if there is a magnetic field and electrical fields. If you want to understand the magnetic fields without any current and so on and so forth. Same way you can also understand heat transfer in porous material, heat transfer in pipes, in fluids. So, you have a multiple options of selecting. Once you select, you can see the selected items in a window which is shown right over here. Okay. So, that is a process that you need to follow. After that, what is a study selection? Study selection is that we are selecting a stationary as an option. What do you mean stationary? So, a stationary study is used when field variables do not change over time. Right. That means that if I apply a constant power or a constant voltage to a heater, and we are not changing any, it is not a variable moment. For example, if there is a cantilever and cantilever is not steady, it is vibrating continuously, I can select the another study instead of the static study, all right, or stationary study. Now, the reason of or what exactly stationary means, it is already given in this particular paragraph, that the stationary study is used when the field variables do not change over time, and the example is in electromagnetics, it is used to compute static electric or magnetic fields as well as direct currents. In heat transfer, that is our example, to compute temperature field at thermal equilibrium, we can use the stationary. Also in solid mechanics, it is used to compute deformation, stresses, strains at static equilibrium, not at dynamic not in dynamic condition. So, let us see, once you do that, the next step is to select the geometry. So, you are selecting a geometry from the component window, and then you can select the length, is it in meters, micrometer, the unit in degrees or what. If you want to go for advanced, the geometric representation is using CAD, and your repair tolerance can be automatic. When you select this item, then the next step would be that you have to select the model parameters. So, what is the parameter that you are using for your selected design? In our case, what is a selected design? The selected design is a heater. So, what we need to understand, what is the voltage that you want to apply. So, here is a voltage, then what is the layer thickness that you are selecting here, what is the layer thickness, about 10 micrometer, 12 volts is the maximum voltage. So, the electrical conductivity of silver we have to select, because the contact, if you remember, are made up of silver. Then we have to understand the electrical conductivity of nichrome. So, we are selecting electrical conductivity of nichrome. Then the temperature, air temperature is the temperature, H temperature, heat transfer film coefficient. Then fluid temperature, because we took an example of a fluid flowing below the heater. So, that is the temperature of that fluid, and then heat transfer film coefficient. So, when you select this parameter, and then you use the so this parameter will be applied to this particular section where you have a glass plate and you have a heating film. All right. So, here we have selected a little bit bigger heater just to explain you up, and when you select a geometry, you have multiple options here also. So, what is square 1, square 2, fillet 1, fillet 2, is it plane geometry or not, and then what is a material. So, what is a material that is on which you are fabricating the heater? Is it silicon or is it a glass or is it some polymer? So, we have option of selecting the material where you have selected here silica glass. You can see here lot of material options are there. You can select glass, granite, iron, magnesium, mica, molybdenum, polysilicon and lot of other materials to be used, or that can be we can select as a substrate. Substrate, you know, that on which we are creating a or fabricating a device, right. So, the material selection is possible by adding the material on the material selection window, followed by, now we want to just select here silver. You see here what we have selected silver, and so this is a material 2. Our material 1 is a glass, that is our material 1, right. So, here it is, you see material 1 which is our silica glass, material 2 it is the silver, right, which is right over here. Then we see material 3. So, material 3 would be the nichrome, it is right over here, right. So, we have 3 selections, one is the glass, one is the nichrome and one is a silver pad. Now, for each of those, if you see, the values would change. For silica you have heat capacity, density, thermal conductivity. For the silver you have thermal conductivity, density, heat capacity, electrical conductivity, relative permittivity, while for the nichrome also it will be same because it is a conductor, right. Now, after this heat transfers in solid, you have to select this heat transfer in solid, and then first you select thin layer 1, right. So, thin layer 1 we have selected coordinated system as global, layer type we want to know is thermal thin approximation, right. And then when you select heat flux, you want to see what is the heat transfer coefficient, which is H air, and if you want to see the temperature it will be T air. So, when you want to further, you have to understand what is the convective heat flux, and earlier what we have seen is we are selecting heat flux 1 and then we are selecting heat flux 2, that is the first one is on the front and second one if you see it is on the another side. Then after that you are using electrical currents, right, that is flowing through this one. Then electrical potential where you will apply, you have to select this boundary, this is what is selected, and then we have said that here we will apply 12 volts, right. So, this is with respect to this. So, this will be grounded and this will be, so voltage is applied between these two pads. See this ground. So, here earlier if you see on the pad 1, that is the silver pad, right here, which is a blue color line, you are applying 12 volts, this one, okay. And then you apply, where is the ground? So, ground is right over here, right. So, we applied electrical potential between two pads, followed by temperature coupling, right, and then electromagnetic heating. So, temperature coupling can be, so electromagnetic heating we are interested in the pattern, right, what is the pattern and how it will be heated up. Then you have to create a mesh, right. So, if the mesh size is extremely small, it will take longer time and you will get a better result compared to a larger mesh. You need to use a smaller dimension in the mesh. After that you are using study phase 1, right, where your step 1 is a stationary, you have selected all the parameters, heat transfers, electrical current, temperature coupling, electromagnetic coupling, right, and then you see what is the temperature. So, now if you see the effect of the voltage 12 volt to this particular chip on which there is a heater, you will see that the temperature distribution, right, over the chip. And as you can see, the maximum heating, that is about 420 degrees centigrade, is in this particular region. There is another parameter you have to understand why the heating is more in a particular area compared to other area. You can also see that it is kind of uniform in the center, right. So, this lies between 400 and 420 degrees centigrade, while the corners are colder compared to the central region because there is no resistor on the chip, right. So, there is no heater. When I say resistor and heater, it is same thing because this is a metal that you have formed a structure, and you know resistor is nothing but rho R equals to rho L by A, right, where rho is resistivity, L is length and A is area. So, you are creating a longer length to increase the resistance, and the resistivity depends on the material that you have selected, which is your nichrome. After this, the next step would be to see the electrical potential. So, you can see when you apply 12 volts right over here, and there is a ground which you can see here, how the electrical potential varies across the resistor, across this resistor, how the electrical potentials are varying. So, that is another thing that you can work on, you can see. Okay. Then the next step would be solid mechanics, and then you have to go further, which is for rigid motion suppression. You have to understand if I apply a stress or a strain to the heater, what will happen. Same thing goes for thermal expansion, right. So, this is what we have seen is, you see here, let us go for here, heating, right, and then you can see the electric potentials, followed by solid mechanics, in which you can see the rigid motion suppression. After that, there is a thermal expansion, followed by a stationary, and so on and so forth. So, let us just understand until here for today's class, and we will follow with another module in which I will explain you further details. So, for today's class, what we understood is that there is a simulation tool called COMSOL multiphysics, using which we can understand the effect of voltage on the heater, and what is the temperature distribution over the chip when you form a particular design. At the same time, we also have seen the change in the electrical potential for the given resistor. In the following class, we will see lot of other things, such as the solid mechanics, and we will see the rigid motion suppression, we will see thermal expansion, we will also see the effect of the stress on the heater parameter, we will see the effect of the so the point is, there are multiple parameters that you can find out using simulation tools. So, let us stop our lecture now. You revisit this lecture, and I will continue for one more module, on which I will explain you the remaining part of this particular simulation. Till then, you take care, have a nice time.